Imagine you're building a computer program that can recognize handwritten digits. You show it a messy, scribbled 3, and somehow, it needs to confidently say, "That's a 3. We've seen how neural networks can make these predictions. They take an image, process it through layers of interconnected nodes, and output probabilities for each digit. But how does the network learn to do this? How does it get better at distinguishing a 3 from an 8? In our previous video, we built up the intuition for how a neural network takes an input, like our handwritten 3, and performs a forward pass to generate an output prediction. We understood the roles of weights and biases in transforming information. But that's only half the story. A network that just predicts isn't very useful if its predictions are wrong. The real magic, the true intelligence, comes from its ability to learn from its mistakes. Today, we're going to unravel the core algorithm that makes this learning possible: backpropagation. So, why do we need to learn? Because when we first initialize a neural network, its weights and biases are essentially random. It's like asking a toddler to identify a 3 for the first time; they'll just guess. The network makes a prediction, and we compare it to the correct answer. For our 3, the correct output should be a high probability for the 3 output node, and low for all others. The difference between what the network predicted and what it should have predicted is what we call the error or loss. Our goal is to minimize this error. To do that, we need to adjust the network's internal parameters, its weights and biases. Think of them as the network's adjustable knobs. If the prediction is wrong, we need to turn these knobs in just the right way to make the error smaller next time. But here's the challenge: a typical neural network can have thousands, even millions, of these weights and biases. How do we know which knob to turn, and by how much, to reduce the error most effectively? We can't just randomly tweak them; that would take forever. We need a systematic way to find the direction of steepest descent in our error. Imagine you're blindfolded on a mountain, trying to find your way down to the valley floor. You'd feel the slope around you and take a step in the steepest downward direction. This steepest downward direction is precisely what the gradient tells us. In mathematics, the gradient is a vector that points in the direction of the greatest rate of increase of a function. For us, we want to go down the error, so we'll move in the opposite direction of the gradient.